Over the course of our study of trig, we have solved increasingly complex trig equations. There's just one thing left to add now, and that's just trig equations that involve identities. So two examples, just to demonstrate this. We have an equation we want to solve here over a particular domain, 0 to 2 pi, where our angle x is in radians. Now if we look at our equation, what we'll notice is that we don't have just one trig function involved, we have two. And so often what you need to do when you solve an equation, not always, is try to reduce the number of different trig functions. So what I'm going to do here is I'm going to take the sine squared and I'm going to try to convert it into a cosine squared so that all of the trig functions in this equation are in terms of cosine. Well, remember, I know from my basic Pythagorean identity that sine squared is 1 minus cosine squared, so I can make this replacement. Do some simplification. And my 1's cancel out. And it's looking like it's going to be quadratic-like. So let's set it to 0. Cosine squared x plus 2 cosine x minus 3 is equal to 0. And that one factors, I believe. Cosine x. 3 and 1, but we're going to need positive and negative, so cosine x is 1, or cosine x is negative 3. And we know that cosine never reaches negative 3, so there's no solution here. Cosine graph only goes between negative 1 and 1. And so where is the cosine graph equal to 1 on my interval 0 to 2 pi? So a cosine graph, it's at 1 at 0 and at 2 pi, but we don't want 2 pi used, so therefore my angle is x equals 0. Now keep in mind that the equation I had above is not an identity. This statement is only true if my angle is 0 radians. Just in terms of graphs, remember, if it's an identity, both sides will produce equivalent graphs. This time it won't, so if I type in the left side and then my right side, and I'm going to set my domain from 0 to 2 pi. Actually, I'm going to move this back a little bit because we know one of the answers is 0. We won't see it otherwise. Let's just put negative 3. Remember, the solution will be the x value of the point of intersection. And so the x value of the point of intersection is x equals 0. We're not including 2 pi because there's no equal on the interval. Here's another equation we want to solve in radians, this time over the set of real numbers, which, remember, means a general solution, all solutions. And if I look at my equation, I'll notice again that I have two different trig ratios. So if I can't always do this, try to get it in terms of one trig ratio. And if I think about cosine and secant, I know that they're both related to cosine. So I'm going to change the secant into 1 over cos, and 5 times 1 over cos is 5 over cos. And this is creating a fraction, so I need to be mindful here with my solution that cosine x can't be 0. I'm not going to be able to get solutions of values of x where the cosine graph is 0, which is at n pi over 2 where n is odd. Okay, we just got to keep that in mind. In terms of actually solving this equation, it's like solving any equation with fractions. Easiest thing to do would be to multiply both sides by the common denominator to clear the fraction. And then if we distribute through, 3 cosine squared x plus 2 cosine x equals 5. And it's quadratic-like again, so I can set it to 0. Hopefully it'll factor, otherwise I may have to use the quadratic formula. Check that out, make sure that if I multiply it out, it gives me what I started with. Yes, so cosine x is negative 5 over 3. And again, we know that a normal cosine graph doesn't go above 1 or below negative 1, so there's no solution coming out of this piece. And again, we have cosine x equaling 1. We were told to remember to be sure not to allow cosine x to be 0. Well, it's not going to be, so that's good. And cosine is 1, as we said in the last example, at 0, 2 pi, 4 pi. In other words, to generalize it, at n pi, where n is even. Or you could say at 2n pi, where n is an integer. Both of those are equivalent. And I'm sure there's other ways to state the solution as well.